Okay, so we are live. Hello everyone, I'm Tarun Jain. I'm a developer and community manager at AI Planet. I welcome you all for the module 2 recurrent neural network and language modeling. So I'll just present my screen. So I'll be the speaker for today's session and as well as the moderator. Okay. I hope my screen is visible. Guys, just make sure, just in chat whether the screen is visible or not. Hello. Uh, is my screen visible?
Hi Tarun, yes, it is visible. Go
Okay.
ahead.
So again, welcome everyone for the module 2 on recurrent neural network for the LLM Bootcamp 0 to Hero in LLMs. So I'll also, in today's session, I'll be briefing about how recurrent model works and as well as what is language modeling, the fundamentals of how you need to enter into LLMs. And then we have a project where you will implement sentiment analysis using PyTorch with LLMs. I mean LSTM. So before we start with this session, again I'll introduce myself. I'm a DevRel and community manager at AI Planet, and along with that, I'm also part of Google Summer of Code 2023 as a contributor to CA Microscope, where I'm working on a project which is related to healthcare. And as a volunteer, I'm also part of Pi and AI Bangalore, a deep learning AI ambassador. So before we proceed, right, many people add few doubts like, I don't know neural network. How do I understand a neural network? What is back propagation and all those things? So let's take a classic ML example. You want to book a ticket. Okay, so whether you want to check the price, whether it is above 50K or less than 50K. So you have a traditional data. So whenever you are working on any classic ML algorithm or any machine learning algorithm, you need specific data. So in this particular thing we will have certain conditions, and this condition can be any features, and this feature can be whether it can be gender, it can be age, or it can be whether he is a family man or whether he's a single, and there might be multiple features and we don't know how many features do a particular data has. And based on this data, now we need to predict whether that particular person can book a flight ticket or not. Okay, so how does it work? Firstly, once you have the data, second, there is little bit of pre-processing step, and once pre-processing is done, this is where neural network comes into the picture, where you are building a model. While building a model, you need to consider few of the algorithms. Now by algorithm, if we take logistic regression, right, for logistic regression we have few parameters, whether it is weights and biases. And once you have weights and biases, there is a activation function. So activation function is nothing but a non-linear function which is used to calculate the specific end value. Now this can be in range of 0 to 1. So if you are using a softmax, I'll show how a softmax looks in the coming slides. So once you have the activation function, now you are calculating a particular value. Now once that value comes, you need to update. Now, okay, so once you do any prediction, right, you get certain value. Now whether this particular predicted value, is it close to the actual value or not? During this process, right, in order to calculate close value with the actual value, you have certain loss. In order to reduce the loss, this is where we use back propagation and gradient descent come into the picture. I won't dive detail into what gradient descent is and how a gradient descent works, but I'll give you a rough picture what a gradient descent is. So let imagine that once you have any loss value, now this loss value might be in very huge, it can be 10, 10.5, but you need a loss value which is very close to zero. In order to do that, you need to update your weights and bias value. Now how do you update it? This is using a gradient algorithm, and you also have a specific value which is called learning rate. Now learning rate is nothing but a step size what you do to reduce your weight value with particular step, and I'll explain you via diagrams in the coming slides. So this is a rough image of what a neural network does and how you can calculate a value based on weights, biases, and using gradient descent you are reducing the loss. In simple term, it is an optimized algorithm. So now let's move on with what is recurrent neural network. So before we move on with recurrent neural network, let's imagine why do we need recurrent neural network. So let's take this example again of a common classic ML algorithm, which is a neural network. In neural network, whenever you are feeding any x and y values, you need your input and output size to be the same. But if you look at different examples in speech recognition or text classification or language translation, most of the time you need the data varies. It can be in different size. In order to tackle this, a classic ML algorithm or a basic neural network model will fail. And next, if you look at the next big problem, you are not sharing any features. Now, what do I mean by sharing the feature? Let's take an example. This movie is great. Now, if you want to feed this in the classic ML model, you have different position of a text. Now, movie is great. So, movie becomes a particular token. I'll explain what token is. So once you have the token value, right, movie and grade, these two becomes two different identical values when you are using a neural network. But if you are using a recurrent neural network, the movie and the grade, so this particular thing will have a position. That means you're sharing the features. I'll explain you what this sharing of feature means using this diagram. Now let's take this. I hope this screen is visible. This particular thing, right? The green which you are looking into. This is what you call a time step. Okay, for this time step, you're feeding your x value, you're feeding your y value, and then this h is nothing but a hidden state. So if you are looking at neural network model, you have your input, you have your output, and you have the hidden state. So this is the same. So once this is done, you have a different text. So if I have the example of this movie is great, my h1 is h2 is movie, then h3 is this movie is, then your last will be great. So now what will happen? I'll just open my drawing board. I'll present my screen. One second, I'll open my drawing board so that I'll explain you clearly how feature sharing is done. I hope my screen is visible, right? Hello. Guys, just
Well,
let me know whether my drawing board is visible or not.
yeah, it's visible.
Okay.
It's just that yeah, it's visible.
Okay. So now I'll just draw a time step. So this is what a time step looks like. Now I will feed my example. Yeah, this movie is great. So I'll just consider my first word, which is. So this will pass into this time step and we will get a tokenized value. And along with this, you will also have a hidden state. Okay, so this will be my h, this will be my y hat, which is getting predicted. Also, we'll have loss function, which is of later matter. But let's now only focus on how recurrent neural network is different from neural networks. Okay, I hope this is really dirty, but I'll again explain this via slides. This is only for basic understanding of how feature sharing is done. Okay, so I'll just use for three words. This is again my x2. This will be my x3. And this again will be my y hat 2, and this will be my y hat 3. So once you feed in your text data, right, this movie is great, you will first pass with the h value. So now what will be this h value? Now, when I tell this movie is great, you're not passing the text data. Instead, you're passing the token value. And after token value, you will have your embeddings. So embeddings is nothing but the word representation. If you have completed the content for the day one, you will understand what is word embeddings and what are one not encoders and embedding layer. So I won't talk much about embedding layer as it was covered in the content for day one. So once you have this hidden state is filled with zeros. So my initial values for h, now h will be zeros. Now once this is done, your first token, which is, will be passed to the second time step. So now what will happen? You are performing certain deactivation value. So you, for each time step, you have certain activation function. So after the activation function, you are getting a deactivation value that is getting passed to the second time step. So again, once this is done, you have one more time step, and this is again moving towards the next time step. And again, after you have this particular time step, you are moving with the last time step, which is great. So this movie is great. Now you have, if you look at the last time step, which is great, it has the context or the feature of the first time step. This is where position sharing, which is feature sharing, is done. And in the classic ML algorithm and the neural network, this cannot be performed. And to solve this problem, or to solve this issue, the recurrent neural network was involved or invented. And the reason is to effective sharing of features in the text data. So once this is done, I'll move on how a recurrent neural network works. I'll again go back to my slides.
Yeah. Tarun, while you're going, so there is a small request from the community if you can slow down the pace a bit. I think that's one
Okay.
request we have.
I'll
Yeah.
just revise this once.
Yeah.
So as we know, in recurrent neural network, the problem which is it is solving is, once you have the neural network, in neural network there is no feature sharing. So if you have a token like is the movie great, the movie and the great are two different identities. In order to recognize both, you need certain features which is getting shared over the complete architecture. So if you have four time steps, as I mentioned earlier, h of 0 is what you mean by it is filled with zero values. It is an hidden state, and your x value is your input value. And you will perform activation function. I'll show what is the function of forward propagation. You're calculating this h1 value. This h1 value is your activation function which you are getting after certain formula. So once you find this value, you will move on with the second time step. In the second time step, you have your second input value, which is movie. And again, in your next time step, you have different value, which is ease. And in your last time step, you have a value which is called great. So for movie to be in the same feature of the grade, you need certain sharing of the algorithm or sharing of the features. This is where recurrent neural comes in, and using the time step, you are performing back propagation through time. And we have two different ways you can perform this. One is forward propagation and one more is back propagation. So first, let's look at forward propagation. As I mentioned earlier, in order to get the activation value, you are performing certain mathematical formula which is called forward propagation. During the first pass, I told, right, h1 will be passed to h2. But how is h1 calculated? So ht, now this t is nothing but current time step. And for our example, let's take h1. So h1 equals to g1. G1 is nothing but a activation function which is called tan h for the hidden layer. So in G1, in our case, G1 is our first activation function, which is our hidden state function, hidden state activation function. Now let's talk about what is this W. W is nothing but weights which is getting added to our hidden state. Then again we have ht minus 1. So what is ht minus 1? I told you earlier, when you want to calculate h1, h2 needs some particular value. So you are filling this h0 with zeros. So h1 equals to tan h. G1, I'll take tan h. As you can see this point, G1 is the activation function, either relu or tan h. So tan h of WH, which is my weights, and then h of 0. H of 0, what is h of 0? It is filled with zeros. Then plus WX. Now, what is WX? WX is the weight associated with inputs, and once input is done, again you are adding your input x of t. So you are multiplying. Now by multiplying, it is a matrix multiplication with your input with the weights, and again wh is nothing but your weights for the hidden function with the initial hidden state, which is zeros, and then you are adding your bias value. So once this is done, you are getting your first deactivation value for the um, time step. So once this is done, you will go in the loop until you reach to the last uh, time step. So once this is done, you will get your hidden state value for h. And what is y? Now y is nothing but you're adding a softmax layer to find this y at. For that, you have wy. Wy again is a weight associated with your output, and ht is nothing but your particular time step. So once you get any value, right, that will be passed to y hat to be calculated your to calculate your output. So again, you are using an activation function. In this case, the activation function is sigmoid. In most of the example, you are also taking tan h, but in most of the example, if you are looking at sentiment analysis, we will be using sigmoid. Okay, so this is how forward propagation works. I'll just explain this again. So you have your time step. In order to calculate h1, you have a certain formula which is for forward propagation. And to calculate h1, you need h0 value. Thus, h0 values is filled with zeros. And for y hat, again, you have one more formula. And for h1, your activation function is tan h. For y hat, it is sigmoid. And now you will pass all the values to your next time step, and by this you are passing the feature values, and this will move on until you reach your final time step value. So I hope this was any doubts in this step before I move on with back propagation through time.
So there is a Tarun, there is a question about highlighting whether this is for the inference phase or training phase, whatever
No,
we are
this is
doing.
for training. You need your model to get some values, right? You're training to get this by values, so
Okay.
it's for training.
Yeah. Thank you.
Any other questions? uh, any other questions, or should I?
That's the only question we
Okay.
have. I think you can.
So once we have our values, so you're calculating your y hat. Now, as I mentioned earlier, you will get certain value once you perform your computation. But is it matching with the actual value? So y hat is nothing but your predicted y value, but is it matching with the actual value? So this is where a loss function will come into the picture. And in order to reduce the loss function, you're adding back propagation. By back propagation is nothing but you're performing the gradient descent. So let's take at the first step, the output layer gradient at time step t. So here you're performing partial deviation. So L, I'll just zoom this bit. So if you look at output layer, you're performing partial deviation. For partial deviation, you're passing your y hat. So this y value, yt is nothing but your actual value compared to your loss function. And once this is done, you have the derivative of g. This is nothing but your second derivative for the activation function. And once you perform the output layer, this is nothing but what your step size. So once this is done, you will add the hidden layer gradient value by performing this particular formula. Again, this delta ht is nothing but you are updating your hidden state value. If you look at this diagram, right, if you want to move backwards, you also need to update your hidden state values, not just your y value. So this is where first you will update your output value, and along with that you will update your hidden state values. So once both are done, you will add the weights. I told there is a step size when you're performing gradient descent, which is nothing but a learning rate. So learning rate is this alpha value. Now, what do we do in learning rate? Why do we need a learning rate? You updated your output layer, you also updated your hidden layer, but we are not updating our weights. In order to update the weights, you are using you are using the learning rate. So again, I'll explain this process. You performed forward propagation and you got certain values, but with compared to the actual value, there is little bit of loss. To reduce this loss and to optimize our algorithm, we will use output layer gradient at particular time step, and also we are updating our h value. And when we are updating y and h, we also need to update our weights, and weights can be updated along with learning rate. Learning rate is nothing but the step size. So once this is done, we are performing both forward propagation and as well as back propagation. So what does this back propagation through time means? Back propagation through time is nothing but you're going back to the previous state. Now going back to the previous state is nothing but you're going back to the previous time step. So that's where back propagation through time comes into the picture. So once this is done, we have different types of input and output mapping. In our case, this example was many to many. And this is not the only example which we have. So here is where I'll explain what are the different feature or different use cases where RNN are used. Let's talk with the first example where it is one-to-one. In one-to-one, wherever you have time series analysis, by time series, there are use cases where you need to find what is the stock market analysis value for today. So this is where you will have specific time series values, and the one-to-one mapping for RNN is for time series examples. Main example is stock market analysis. Now one to many. In one to many, your input is an image. So that is just a single entity. Now this single entity is nothing but your image, and many is nothing but your caption. If I upload a cat sitting in a bathtub, so this is the image, cat sitting in the bathtub, and cat sitting in the bathtub is the caption which you will get as the output. So which is many. So one to many is where you will have your image captioning and as well as speech recognition. So speech recognition is where you enter any speech and you will get some output. And for many to one, so you have a movie review, and for this movie review you need to find whether it is a positive review or a negative review. The output is just one, either 0 or 1. This is where many to one comes into the picture, and it is a sentiment analysis. Now let's talk many to many. So this is where encoders and decoders come into the picture. For encoders, you're passing the English text. So I'll take the example of language translation. You pass your English text to the encoder block. Then we have a decoder block, which has in the text. And your output is nothing but your decoder block where you will get your in the output. So once this is done, this is the example of language translation many to many. Then we have one more example for many to many, where each and every frame is getting passed as the output. This is where video classification come into the picture. So these are the 5 different ways you can represent RNN. One is one to one, then you have one to many, then you have many to one, then you have many to many. Many to many has two features. One is you have encoder and decoders, and one is frame by frame, which is for video classification, and encoder and decoders, which we will look into module 3 for attention, is for language translation. So let's talk about what are the drawbacks with the vanilla RNN. So for the vanilla RNN is nothing but a simple RNN architecture. We have two major drawbacks. So one major drawback is the gradient descent value. For the gradient descent, most of the time when you're performing back propagation, you get values which are negligibly high and few are very low. So if you are getting high values, it is nothing but your your algorithm is facing issues of exploding gradient descent. Exploding, you have your exploding a gradient problem. And your second feature, if your gradient values is getting very less than zero, so or it is giving zeros all the time. Now what does it mean giving zeros all the time? When you're performing this back propagation, right, you are updating your h value and as well as y value. If it is giving values which are very close to zero all the time, then this is where vanishing gradient come into the picture, where you have your derivative values for the next step iteration as well, it is not getting updated and it is low to zero. So this is where step value has no influence your weights for updating the weight. So gradient is vanishing gradient descent is the problem while running a recurrent neural network. In order to solve this, we have three different features. The first step is you can use any initialization, now weight initialization techniques, to get what should be the H0 value. In our case, we just use zero, but there are different weight initialization technique which we can adopt. And the second one is GRU. Now GRU stands for Gated Recurrent Neural Network, Gated Recurrent Unit. So what does GRU do? Let's take the same example of recurrent neural network. So once you are doing the forward propagation and as well as the backup propagation, you're getting certain values, but you're not updating or resetting few of the values based on the context. So this is where GRU comes into the picture. It has two gates. One is update get and one more is reset get, which holds the value of your context. Now this context is nothing but your candidate hidden state. Now if we talk about this, right, how does it hold? So here we have one more cell which is called as C. If you look at the content, you will have all this available. Now this C is nothing but your memory, memory cell. Now memory cell has the C value. So once you pass the C value, h t minus 1 will be your C value. Okay. So ht minus 1 will be your C value. And once you pass in, you have a candidate value. So this candidate value is updated based on your update gate and as well as reset gate. So for both update gate and reset gate, you have a activation function. For activation function, as you can see, this sigma value is nothing but sigmoid. And again, this sigma value is nothing but this sigmoid. And you have a tan h function. Tan h function is for candidate gate, and this is your final output. And if we look at the drawback of GRU, in most of the cases, there is only few mechanism where you're not storing any values. So now you have, okay, where are the text? Okay, so I'll just tell you why LSTM is used. LSTM stands for long short term memory, and in GRU there was only two gates, two mechanism. One is update gate and reset gate, and in LSTM, you have an extra layer which is nothing but what you call as forget gate. In forget gate, again, you have the updated cell value. So this updated cell value is one more gate which stands for UR. UR is nothing but you keep track of the relevance of that particular context. And the four different formulas which we use in LSTMR, one you have your forget gate, and one more you have your update gate, and one you have your reset, which is your reset gate, and one more is your output state values. And I'll share all these things in the content page of LLM Bootcamp, and I won't dive much detail in how LSTM mathematics works. And the only thing it differs is the formulas. Rather than formulas, each step remains the same. In terms of formula, you will have two additional formulas for get gate and update gate, and rest two formulas will remain same, which is similar to your back propagation through time. So now let's look at language modeling. What do language modeling mean? So let's take this recurrent neural network. We looked at different formulas, like we looked at different mapping. One is one to one, then we have one to many, then we have many to one, many to many. Let's talk about LLMs. For LLMs, what is the major problem statement? You enter any prompt, you are getting certain text, which is text generation. How are you predicting whether what should be the next text? So this is where the probability comes into the picture. Let's take a random context. So this is my example. I love One Piece manga. EOS is nothing but the end of your sequence. Now, in your first time step, what you're passing is the A naught. Now, A naught is nothing but your H naught value. And here you have X1. Now, X1 is my input value, and Y1, Y hat is my output. And as you can see, for each sentence, you will have a probability. So, what should be the next word? So, this is what language modeling mean. Language modeling is nothing but a mechanism to predict what will be the next word which is getting generated. So we have P1. So once this is done, the next word is I love One Piece. So here, this is the current word for the time step, and I is the previous word. So you are calculating the probability based on that. And also, one thing to notice is previously we had x1, x2, x3, and x xt. Xt is nothing but for n time step. In this case, if you can see, after x you have y, which is nothing but you're passing the previous state value. Now previous state is nothing but the time step. Now I love 1, I is nothing but your previous value. If you look at the next time step, op, this is nothing but one piece, and I love is nothing but your previous context. Now unknown. Now what is this unknown? Let's take the example of neural network again. You have a lots of corpus of data, and once you're training this data, there are few new words. Now what is the new word? In my data, manga is not included in my data, so this will be unknown, and that's the reason why I have added unknown. Now after unknown, this three dot is nothing but I love One Piece. In order to if there is less space, so I'm not included. So this is unknown for the manga word. Then this will be I love One Piece. Then again, the last time step will have EOS. So this EOS stands for the end of context, and or the end of sequence, and this triple dot is nothing but my entire example. So what does this p mean? We are just calculating the probability for what should be my next word. So this is the context or overview of what a language model means. In the module 7, we will look at how you can generate this next word using the LLM models or open source LLM models which are available. So this is all about the presentation which we had, and I'll move on with the project, which is sentiment analysis. Before that, you can scan this QR code AI generated to join our Discord channel. Any questions before we proceed with the project? Hello. Hello. Okay. So I'll just take few questions. Why using OP abbreviation rather than full token? Okay, so this is in the context of the probability. As I mentioned earlier, there was no space to add the entire context. That's the reason why I just use OP. In general, it is one piece, the complete text. What is the input in this example? So can you tell regarding what is this context? Hello. Gopal, okay. So since there is no more context to this question, why is the input? What is the input in this example? The last example, you mean the language modeling one? Okay, so I'll just explain this again. The last example. So I'll share my screen again. Okay. So I'll just explain this example again in order to get the context. This is just a dummy example which I'm providing for the language modeling, like how the context is getting saved when you're using a language model. So this will be my first time step and it will take the first word. Now my first word is I. So X, if you are looking at this example, X will be your token value. A0 again will be your zeros filled with zeros. And H1 will be your activation function values. And Y1 again will be the softmax. So whatever probability you're calculating here, it is also using a softmax activation function. Now softmax is a new activation function which I've introduced in these slides. Previously we looked into tanh, then we used sigmoid. For p, in order to calculate this p value, we will use softmax. Now whatever output you get in this p will move to y1. So y1 is my new value and it already has the context of I. So I is nothing but my old word which I already has a probability value. In order, now you need to check what is the probability value for love in context to previous text which is I. Now many people are getting confused why I used OP. The only reason why I used OP was there is no space. OP is nothing but this complete text, one piece. So I just use short form and there is no particular reason for that. The only reason is there is no space to add the entire context. So that's the reason why I have used OP. OP, there is no n grams which is getting involved. Directly, we are passing each word for each time step. And I love is nothing but the previous context. And in this case, why it is unknown. Now, unknown is nothing but you have already trained a model. And by training, not trained a model, when you are performing tokenization, it will only take few sequence. Say you have only taken first 1,000 tokenization. Now whatever new value we have, which is more than by this 1,000. Now what does this 1,000 mean? Each 1,000 is nothing but one particular value. It can be I, it can be love, it can be one piece, it can be any word. So we have 100 tokenization values or 1,000. If you have 1,001, so this is something new to your tokenization value. And manga is a new value. That's the reason why I've given unknown. Now again, this triple dot means I love One Piece, and EOS is end of sequence. This triple dot is nothing but I love One Piece manga. So that manga will be unknown. So this is where this triple dot will have my context. So once this is done, now you want to find out what will be the next word. So that is where you will use this particular use case. So I love One Piece manga written by Ichiro Oda. So this might be the complete output for this particular example. So we are only providing the sample text by adding the end of sentence so that it will understand, okay, So I need to end at this particular time step as I've already encountered the end of sequence. So I hope that answer is your question. Okay. No, I'm not using ngrams for language modeling. How do we determine EOS when we do know the unknown yet if it is going to be more than a word? Okay, so this end of sequence is given by our input value. So when you are giving a prompt, you enter a text, and once it finds the end value, so the end value is nothing but your manga. So once manga is done, it will add the end of sequence. So talking about UNK is when you are tokenizing it. While tokenizing it, you are doing it on the inference. That means your unknown is already your unknown word manga. It is not there in tokenization. Thus, it is adding unknown value. By unknown, unknown is not the end of sequence. Unknown is just providing that this particular word is not there in our context. So it is unknown. Now, end of sequence is where your sentence ends. Not on once you encounter unknown. That doesn't mean that you are providing end of sequence. So can you explain weight initialization and weight stemming once again? Also on that forward and backward propagation formula. Okay. Okay, I'll just explain how this weight initialization and weight training is done. I'll share my screen again. Okay, so let's take a time step. Now, while you are taking a time step, right, in the new example, you have your own data. Before we move on with the own data, we need to add few certain values. You need to initialize your hidden state. Also, you need to initialize your weight values. So, talking about the weights initialization, we'll start with H0. So, H0 is nothing but your zeros. Now for H0, you have W, which is associated with this line. So for H, you have WH. Now WH will be zeros again. So for WH with H0, you are doing a matrix multiplication, which is a dot operation. And once that is done, you will have your H1 value. For H1 value, this is the formula. As you mentioned that the backward propagation and forward propagation needs to be revised. HT. Now let's take HT to be 1. H1 equals to G1 is nothing but your activation function. WH is your zeros. You will fill initialize value. I'll show this code of RNN on how you can use this WH values, WX values, and as well as WY values. But in these slides, if you are using H0 value, it is filled with zeros. And H value, if you know uh, matrix multiplication rules, your WH value should match with your second column, should match with your rows of the H0. So now H0 is nothing but your hidden state, initial hidden state values. You will do the dot product, and then again, when we look at WX value, it should match with the row of XT. So now XT is nothing but your input value. So input value is nothing but your tokenization output result. I'll show this via code so that it will be more simple. I hope my Jupyter notebook is visible. Hello. Okay. if you look at this Jupyter notebook, right, wx value, you're adding few random examples, and same goes for wh and same goes for wy. This is where the initialization is done, and then you're adding this example. This is your activation function. Then you're performing the dot operation. Now if you look at these two example, the size should be the same. How the size will be the same, you can check at this input shape of 2, then hidden size is nothing but your h value, and then you're performing the dot operation, and training takes place. This is for the forward propagation. This is where your forward propagation training is done, and then you're doing the loss identification, and then you have y values. So once that is done, again you're calculating your this is where the partial deviation will come into the picture, which I've mentioned in backward propagation through time. This is where you're doing the partial deviation for your weights value for output and as well as hidden. Then you're updating the weights. Updating the weights is nothing but wx you are updating, wx also you are updating, and wh. So self.lr is nothing but your learning rate, and this partial deviation is your previous weight values. I hope that answers your question. For h2, the input is pht minus 1. So what is p? There is no new values as p. Is this in the context for language modeling or what? Will you demonstrate a code example? Yes, after this I'll demonstrate a code. So as you mentioned, how to use it if we have a token value or answer lies in token beyond 1000. So this is where you need to assign the vocabulary size. When you're doing the model building, you have an embedding layer. For embedding layer, you assign two values. One will be your vocabulary size, and along with that, you have your hidden state. In our case, the maximum value is 10,000, but in most of the case, few people give 5,000, and in most of the example, you have 10,000. So this is where you assign your vocabulary size, and if your token is not there in your vocabulary, then it will give unknown. Apart from that, it won't give unknown. I'm afraid the LLM example lacks. If I assume the input is tokenized, yeah. So if you look at that language modeling example, right, the input, whatever is you are passing, the I love, so the probability is performed on your tokenization value of I. So I'll just clear you one more time. So this I is nothing but your tokenized value of I. So again, P of love, this love is the tokenized value of love. And again, this is the tokenized value of the value. When you're doing the probability, we will work with the context of the words rather than the sentence. So all whatever you're seeing, right, in order to reduce in order for the basic understanding, I've given the text rather than the probability values. So obviously it will be the tokenized value. Tokenized value of I, the tokenized value of love, same for one piece and same for unknown. Unknown will be zero most of the case. Whenever you are doing the tokenization, and when you do this, when you set the default size, unknown will be zero or one. I'm expecting that the model should output. So this will depend on the corpus of training data which we are training on. If the completion of the sentence doesn't match with our input sequence, then it will give some random examples. rather than the exact context. So it depends on what data we are working on. So it doesn't mean that it will add, oh, good to know. Rather, it will use what corpus of data we are training on, that particular sequence, and on what tokenization the tokenized value is trained on. So the X is the result of sort of passing our prompt through word or embeddings or vocabulary. What do you mean by X? When you're performing this embedding and vocabulary, you will just assign the value size rather than any context. So by embeddings, I mean embeddings is nothing but your word representation. For word representation, what will be your vocabulary size will be the IDs. I'll show this in the code example how you will get your vocabulary size, and as well as how it is passed in embeddings. So it will be clear when I show the code demo. H and Y, and as well as how the forward propagation is done, and as well as the backward propagation. So I'll start off with this code. And again, if you look at this example, it is similar to what I explained. You have your H0. H0 is nothing but your hidden state value, which is the initial values, which you will fill with zeros. WH value is nothing but your weights, which you will randomly initialize it. As one of you mentioned, how weights initialization and weights training is done. I'll show it in a code demo. And once this is done, you will find your H1 value. Now H1 value is nothing but your activation value which you're doing. And once activation value is done, you're passing the deactivation value to the next time step. So let's prepare our data for this particular thing. I'll just run this. Your total step, we are creating a sine wave. Sine wave is nothing but one-to-one mapping of RNNs. I'll just run this code. So now if you look at your X shape, I'm doing the numpy. Now, if you look at the shape, it is 225 cross 25 cross 1. Now, this will be my input value. Now, output value is nothing but my y, which is the actual value. Here, since it is the list, it gave error for shape not initialized. Shape error. Now, once this is done, we have our input value, we have our x value. Now, let's come to the RNN part. Now, what will be the input size? Input size will be our X shape. Then output size. Output size will be the dimensional, which is nothing but the Y value. Then we have the hidden size. Hidden size is nothing but the X0 value. Now, once you assign your H value, X value and Y value, we need to initialize the weights. Now, weights is nothing but the random initialization. And once the random initialization is done, you need to make sure the shape is matching with your X value. Now, activation function is nothing but your forward pass. You need a separate function. Now, you can do this inside forward propagation if you want, but I'm just assigning this activation function to be out of my forward propagation so that I can call it anytime I want. So, this particular formula, tan h, so Wx is nothing but my weight of x, and h value, and h t minus 1 is nothing but my previous hidden state value, and y hat is nothing but the dot operation, and self of wy is nothing but my weights initialized, and this ht is nothing but my deactivation value where I'm getting after the forward propagation. Now in forward propagation, you are going till the end of the time step, and once that is done, you will get your predicted value, and you will find the loss. Now for the loss, you will calculate the self dot error. Self dot error, we have calculated it. WY of So this is our new value. Sample output is nothing but our actual value. We are directly subtracting it, and 0.5 is our. This is for the square root of our self dot error. Self dot error is nothing but your predicted value minus the actual value. And in backward propagation, you will update your partial derivation of wy, then partial derivation of wx, partial derivation of wh. So these three are my actual values, which will be later updated using the learning rate. So this particular thing, nb.clip. So this is where you're adding your gradient clipping. For gradient clipping, this is used to tackle exploding vanishing gradient problem. Exploding gradient problem. So once the clip value you are adding, you are updating your weights using learning rate. So learning rate is nothing but your step size. And once this is done, you have your epochs. Epochs is nothing but how much time you should run your model. In each epoch, you will reduce your loss, and as well as you will improve your accuracy score. And testing is nothing but you're adding your new text results, and you're comparing your results with the actual value. And in our case, we are taking 128 to be the none size value. By 128, it is in 1D array. That means h0 will be 000 for 128 times. Then this RNN training is nothing but this is my epochs value, and this will be my learning rate. And once this is done, again we are creating a new test sample. Why do we need a test sample? For testing, again we have taken self.x, self.y, which is the two new complete different data set, which is not seen in our example. If you look at this example, right, I'm starting with total size of 4,000, and then once I'm starting with 4,000, I'm taking after 300, sorry, 400 is my total size. That means I'm taking my sine wave for the total size of 400, and I'm taking my test samples from 300. Why 300? Because in my training data, I've already taken first 250 values, which is already it is trained. So I'm taking after 300, which is the new data which it needs to be generalized on. So once the testing is done, the outputs is getting updated, and we can add it in a predict variable. And this is the loss through each epochs. Now epochs is total 15. For each epochs, the loss is getting reduced, as I told earlier. And this is the actual value. And this orange value is nothing but the predicted value for the time series analysis. So if you look at the time, if you look at recurrent neural network, it also has a use case for one-to-one mapping. It uses time series. For time series, we have sine wave. So I've also written an article on how you can predict stock market analysis. I'll just attach the link to it, which again it is using a recurrent neural network but with TensorFlow. And orange is nothing but my predicted value, and blue one is nothing but the actual value for the sine wave. So this was how you can implement a recurrent neural network from scratch. If you have any doubts, then we can move on with the sentiment analysis project part. Okay. So what's a deactivation value? Deactivation value is nothing but we have h0 value. Then hi value, whatever you get for h1, that output result is nothing but what I call deactivation value. Where can we get this notebook? Add this. I'll add this in the LLM Bootcamp content so that anyone can find it. Okay. Any questions? So this is the last phase of recurrent neural network where we will use LSTM. LSTM stands for long short-term memory, and we will use IMDb dataset to work on sentiment analysis. So we will take the datasets from Hugging Face library. We'll change the runtime to be T4. And we will be using PyTorch, as we mentioned earlier, that most of the modules which we will look into the future, it will use PyTorch, so that it's better to practice how you can start using PyTorch. And then you can set a seed value. This is the best practice because in most of the Kaggle competition, whenever you are adding new generalization of new text, you need certain answers which should be same every time. So it's a good practice. To add a seed value. So what should be the seed value? It can be either 0 or it can be 42. Most of the time, in most of the examples, you will see 42. Now coming to the next step, device. You can either run on CUDA. CUDA is for GPU, and it's better if you run on CUDA rather than CPU. Google Colab supports. Now, how can you run your co- notebooks on GPU? The simple step is go to Google Colab, then check on runtime, then change runtime, then select T4 GPU, which is free of cost, and A100s and V100s. It has certain. You need to update your Google Colab into Colab Pro. So in our case, T4 is good for RNN. So, in order to switch into GPUs, you need to check whether CUDA is available or not. And in order to do that, you can use torch.cuda is available. Else, you can use CPU. So once this is done, now we need to download our library from Hugging Face, and we will separate our training data and testing data. So once we have our data, what was the first step? First step is we need to tokenize it. And how do we tokenize it? For PyTorch, we have a library called Torch Text. It's a library which is made for NLP, where you can do most of the pre-processing step, which is involved in text data. Now we have tokenizer. Tokenizer is nothing but you want to convert your input data into a token value is nothing but you have your string value, it will be converted into a numerical value. This is what you mean by token values, and each text will be unique value. So if you have I which is repeated twice, it will be considered as a single token. Now we will tokenize our complete text sequence, and we will do it for both training data and as well as test data. Now this map is nothing but you are using this function to map your training data, and since we are using data sets from Hugging Face, this particular variable will have map value. This map value will map our text sequence into a tokenized value which is a numerical value. So once this is done, after tokenization is done, we will directly split our data to avoid data leakage. And once we add the data leakage, in my slides, I told that if there is any word which is not there in the sequence, we need to use unknown. By unknown, we mean UNK, which is not seen in our input sequence. Now, padding is nothing but not each review will be of same size. Few of the text sequence can be of just 5, few of the text sequence might be 10, few of them might be 15. In order to make the context constant size, we will add the padding value to be zeros. So these are the two special tokens, and again we can use torch text to do all this pre-processing step for us. And I told you earlier as well, whenever we are doing unknown, the tokenized value for unknown will be set as 1, and this is the zeroth index for unknown value. Now vocab is nothing but the PyTorch torch text variable. Now once this is done, now we will prepare our data set so that we can feed this into the model, and we will normalize the text. By normalizing the text, the only thing is we will get the IDs value. What do the IDs value mean? We have the example. Now example is nothing but your text sequence. Now you will get the token value, and IDs is again it will map as a dictionary. So dictionary with the IDs value which is unique. Now once this is done, again we will map with the tokenized value, and we will make it in a suitable format so that we can feed it in our neural network. So this is how our training data will look into. We have a length of 256, which we had already initialized. 256, and this is the tokenized value. As I said earlier, IDs, we will feed in all the tokenization values. So this is where IDs is stored. We are normalizing our text sequence with the IDs value, and this is how the tokenization looks. Now once you prepare your data, I'll just revise this step. First you will load your data. Once you load your data, you will tokenize your values. Once you tokenize your values, you will prepare the data. Why do we need to prepare the data? In order, the main reason I need to prepare the data is it should be suitable so that we can feed it to the model. So once you prepare the data, here is where you will do the model building. In model building, first step is you will do your embeddings. So one of you had asked what should be the embedding size values. This is where you will add these two values, vocabulary size, and again your embedding dim. Now this dim is nothing but the dimension values. It will be any 64 or 128 or 256. Then once you do the embeddings, then you will add it to the LSTM block. Now, why do we need this? Can't we directly pass the tokenization value into the LSTM? Because once you look at the word representation, in order to do the closeness value, you need the embeddings layer. And apart from embedding, one more option is one-not encoding. Why do we don't use one-not encoding? It's because we want to reduce the dimensionality, which is curse of dimensionality, and that's the reason why we are using embeddings. So once that is done, we will use a LSTM function. For LSTM function, now let's talk about what is this n layers. In neural networks, we have multiple layers. For each layer, we don't just need a single LSTM function. We need multiple LSTM. That's the reason why we will use this N layer. Now, by bidirectional, you mean if you're going frontwards, we also need the backwards as well, so that it will hold the positional features. Now, dropout rate is to reduce overfitting. And again, if you learn neural network, all these terminologies will be simple. Dropout rate is nothing but a technique which is used to reduce overfitting. So once this is done, we will get a certain numerical values, and we will this might be in 2D or 3D. We will pass it into a single linear function, and then we will use a output function, which is nothing but output function is our FC. So this FC is nothing but our output function, which is fully connected layer. This is called dense function. And once again, this dropout is nothing but you are reducing the overfitting. Now how do you map all of this? This is where forward function will come into the picture. In PyTorch, once you build a model, uh, along with the model, you also need to initialize this forward function. In forward function, you will stack this padding sequence. By padding sequence, you want your each text to be of the constant size. So once that constant size is done, you will use the LSTM function. Now LSTM is nothing but this particular function, uh, layer, not function. This is your layer, LSTM layer. So once this is done, you will use the bidirectional. Bidirectional is nothing but you're going frontwards. We also need the backwards feature. So once this is done, we will add our output layer. Hidden is nothing but what should be our total dimensional. So now coming to the vocabulary size, we will check what is the total vocab size. Then embedding dim, it's nothing but a normal numerical value. You can set this any value. This can be any value from 64 to 128 to 256. Again, this can be any value or 256. So these are the constant size which we use. And then output dimension is nothing but what is my label. This will be a sentiment. So either it will be zero, either 0 or 1. The length is nothing but 2. Now output layers is nothing but how much LSTM layers you need. Now bidirectional, whether you need bidirectional feature or not. And dropout is nothing but layer which is used for reducing the overfitting. Now once you have all these hyperparameters, you will feed this into the model. And then this total parameters. What are these parameters? Parameters are nothing but the weights and bias value, which we will calculate, which is more than 10,000. No, this is 10 million trainable parameters. That is nothing but your WH, WX, and WY. And also we have forget get and as well as update get weights. So once this is done, we need to initialize the weights value. And there are two ways you can do this. One, you can use a different function, or you can use if here you have def init weight. So this is one more function you can create, and you can initialize the weight inside this. If not, you can do it outside your LSTM model. So once this is done, we will apply our initialize weights, and this is how our model looks like. First, we have embedding layer, then we have LSTM layer, then we have a linear layer, then we have a dropout. Then now this is where we are adding extra pre-trained embeddings. This is extra pre-trained embeddings. Now, why do we need this? In most of the cases, if we have very less data, we might require more number of embeddings. This is where we will use these vectors and fast text, which are pre-trained embeddings. And once this is done, we will convert these pre-trained embeddings into the vectors with the token values so that we can change our model embeddings. As you can see, we already have an embedding layer, but we are using a pre-trained embeddings, which is trained on a very big data. Then we will take the token values and we will update the weights of our embedding layer. Now, once our model is built, we need two main optimizers. Now, optimizer is nothing but algorithm for gradient descent. Now, criterion is nothing but our loss function. So this is our loss function, which is cross entropy, and our gradient descent algorithm is Adam. What are the available different options? One you have is Adam, then you have this gradient descent. One more is you have RMS prop. Now, what are the different criterion? Either you can use binary cross entropy, or you can use cross entropy directly. So these are our loss function, which is nothing but criterion. And now if you can see here, we are using device, that is we will switch our model training in GPU. Now we will again switch our loss into GPU. So this device is nothing but our GPU or CPU. So now once this is done, whenever we get a new data, if there is a new text sequence, we need the pad sequence to happen. So this function is for that particular thing. And now we will load our data loader and valid data loader. So why we are doing this train data loader, valid data loader, and test data loader is nothing but we already have our training data. So if you can see, we already have our training data in order to send as a batch size. So this will be in a single sequence. So we need to send it as a batch so that the model training is done in a very quick pace. So this is where we will use the data loader. So data loader is a pre-built libraries which are supported by PyTorch. We will do it for all three: training dataset, validation dataset, and testing dataset. So this is where we will have our model in a batch size. Then we will use it in a train. So training is nothing but you will train your model. Now epoch is nothing but how much time you will run to reduce your loss. So once this is done, you will uh, so this is where you have your batch length from data loader. And for prediction, this is the y hat value. Y hat, I'll just write y hat, your prediction from the model. If you look at our previous slides, right, we had a time step. It will give us a y hat value. So this is where you will get your y hat value. And once this is done, you will do the loss function. Now, what is loss function? You will take care of both and actual value and predicted value. So what is our actual value? Our actual value is the label, and our predicted value is prediction. So once this is done, we are able to calculate our loss, and then we will find the accuracy score. By accuracy score, you're just adding again one more formula. Then this is where you're using your optimizer. In our case, it is Adam. Here is where you'll do the gradient descent, and we will now optimizer dot step. This is where we will update the weights with the learning rate. If you know PyTorch, right, these steps will be very simple for you. And these are the flow on how you need to train a neural network in PyTorch. Then again, you will use a evaluate method. Evaluate method is similar to whatever we did in training, but instead of model train, we will write model.eval. Where is it? Model.eval. And we need no optimization for this one. By no optimization I mean there is no step, no update in weights. Remember one thing, we will update our weights only during training and not during inferencing. By inferencing is nothing but evaluation. And again, once evaluation is done, we will do check the accuracy score. And now we will run it for the epochs. We have already defined the train and evaluation function. We just need to call those function and run for each epoch. We have only taken three epochs. We will run it for each epoch. As you can see, we have around training loss, which is very close to zero. And again, validation loss is also close to zero. And both training loss and valid loss, it is 0.6, 0.6. That means we are neither overfitting or underfitting it. And our accuracy score is around 78%, and loss is zero point 0.4, which is pretty good. And once this is done, We will run it on a new data. New data is nothing but amazing movie, loved it, and you will call your predict sentiment. By predict sentiment, you will run this tokenization value, and you will call your model, which is already trained. You can also save your model. So this is where you will save your models. So you can also save the values, and you have predict sentiment where you need to predict on the new values. And this is our input text, and this is our input text. And predict sentiment is nothing but this particular function which is getting called. So if you have any doubts, I'll share this source code with everyone. Hello. Okay. So, dear speaker, my request for an elaboration for the difference between the roles of tokenization and embeddings in this code. So, let's talk about tokenization. We have our text sequence. So, what is our data? Our data is a input, which is a text. Now, this text is nothing but a movie review. For a neural network, we can't pass string input, so we need particular tokenization value. So you will convert your input text sequence into a numerical value which is very unique. So once you have your tokenization, now you are moving on with the embedding layers. For the embedding layer, you are passing the tokenization value. During embeddings, you are performing for particular word what will be the closeness for the next word. So this is where you will add the embeddings function. And tokenization is nothing but the conversion. Embedding is nothing but you will create a vector sequence. By vector sequence is nothing but a numerical value which will be in range of -1 to 1, and tokenization values will be in range of 0 to 1000. Okay, so this was already covered. So is there any more questions, or should we wind up? I'll share all these resources so that you can check it out. uh, do we have any more questions? Maybe visualize the tokenizer output and the embedding output. If you print tokenizer value, right? I'll just run this program. So this is how your tokenizer value looks like. It will be 14, 18. So now this 14 will represent certain word in your particular sequence. Now 14 might be any word, again 18 might be any word. For this particular train data, 0 is nothing but you have any movie review. For that movie review, you have this particular token size. So this IDs, how this embedding layer will look like is nothing but it will be 0.5, 0.6, and by 0.5, 0.6, or any numerical value, it's nothing but a vector function which will be of a 1D array, and that entire thing you will pass it to the embedding function. Now embedding, I mean the LSTM layer. Can we use one-not encoding and our input since models understand numerical value alone? So as I mentioned earlier again, for one not encoding, you will increase your dimensions. By increasing dimension is nothing but you will end up into curse of dimensionality. In order to reduce that, we will be using embeddings layer. So we have added all these things in the module one. What is difference between word embeddings and as well as one not encodings. So these are the two word representation, and the disadvantage between one not encoding is nothing but curse of dimensionality. We'll take one last question if there is any questions, or else we'll wind up. It's late already. Okay, I guess we can wind up. Okay, is there any normalization steps in the code? Yeah, we do have normalization step, and this will be taken care by the torch text, which is our PyTorch library for reprocessing your text data. We don't have any session tomorrow. It will be next week. We will have live session only on weekends. In meanwhile, most of you can take up PyTorch course because PyTorch is what we will be using throughout our sessions. Uh, okay, I guess we'll. Okay, any books? There are two books you can look into. The first book is by Ian Goodfellow. He will explain you the entire deep learning with mathematical formulas. And one more book is Deep Learning using PyTorch. And this book you will be able to learn PyTorch from zero to advanced level. One is Deep Learning by Ian Goodfellow, and one more is Deep Learning using PyTorch. Uh, I guess we'll end this session. For more updates, we'll use Discord channel.